this section is optional, so if you're starting with Python, you might simply skip this section. The idea of this section is the following. So above we defined the function fixed point in this way, where we say the output level of the first firm should in equilibrium be equal to its reaction, its optimal reaction to the output level of firm 2, and the output level of firm 2 should be in equilibrium equal to its optimal reaction to the output level of firm 0. So if fixed point is equal to 0, I managed to get each output level equal to its optimal reaction, and that's called a Cournot equilibrium. It's a Nash equilibrium. So this function is well defined, but it's only defined for the duopoly. If I would now like to calculate the equilibrium, the Cournot equilibrium with 3 firms, I have to define a new function fixed point for 3 firms, or a new one for 4 firms, etc. And indeed, in the notebook, that's exactly what we're asking you to do, to change a function fixed point for 3 firms into a function fixed point for 2 firms. But clearly this is not very efficient. It would be better if my function fixed point would simply be able to handle any number of firms. So not pre-specify it as a function, a fixed point function for 2 firms, but simply leave it endogenous and check how big the vector Q is. So how many numbers, how many firms we have in the market, so how big n is, and then calculate the fixed point for that case. So that's what we're going to program now. So basically what I want is I want to define a function fixed point which depends on Q and C, and which can then simply be specified as returning Q minus reaction QC. Yeah, so we don't have this Q other thing there, it's simply a function of Q and C only. Now in order to do that, I'm going to define the function reaction as a function of Q and C as well. And I'm going to assume that somehow I can figure out what Q other is, and I'm going to define later on how that is done, but now I'm going to assume that I have a function Q to Q other, which from the vector Q calculates Q other for each firm. And then the optimal output level for each firm is going to be determined as follows. I'm going to do my fmin bound from the SciPy optimize library. So I'm going to specify in a second what this thing is going to be. As above, I need the first element of what fmin bound is going to give me. It's going to give me a list of numbers. I need the first element of that. And then I'm going to solve this for I in range the length of Q. Yeah, so normally I would say I would like to solve this for 2 firms, 3 firms, but I don't want to specify how many firms I have. So we'll simply look at the vector Q that's given when the function reaction is called, and I'm going to do this optimization problem if the vector Q has length 5, so that means there are 5 firms in the market. I'm going to do this optimization 5 times for each of these firms. Yeah, so I don't need to pre-specify as I did in the example here that I'm going to have 2 firms, 3 firms, or whatever. I'm going to simply run the optimization for each firm that happens to be in the vector Q. So now how do I specify my fmin bound? So again, I'm going to use this lambda function. So x is going to be the output level of firm I. So we can't maximize, so we're going to minimize minus profits. So what are profits? It's going to be 1 minus x minus Q other. And this is going to be Q other of firm I. Yeah, so I haven't set yet how we're going to figure out what Q other is, but here I'm going to do this for firm I minus the cost level of firm I, and of course there needs to be an explicit multiplication here. So this is my optimization part. Then we're going to look for the optimum between the bounds 0 and 1. And I'm going to specify that I want full output equal to 1. And then I'm going to return Q star. Yeah, so this gives me reaction. And reaction here hasn't specified how many rows there are going to be. I'm using this trick here where I use the range of the length of Q. So if the length of Q is 5, range of Q is going to be 0, 1, 2, 3, 4. So we're going to loop over all 5 firms when we do this optimization here, this maximization of the output. So now what I need to have is this function Q to Q other, which is a function only of the vector Q. So I need to know how long this is. So the length is going to be the len of Q, so the length of the vector Q. And I'm going to return the following. It's going to be an array. And I'm going to sum the output levels of every firm except firm I. So how can I do this? I'm going to look at the vector Q and I'm going to define a Boolean mask that includes all firms except firm I. So how can I do this? So I can use here numpy arrange for length. Yeah, so I've defined length here. So if Q, the vector Q has length 5, it means I have 5 firms in the market. I'm going to have here numpy arrange 5. So it's going to be an array of the numbers 0, 1, 2, 3, 4. And I want to sum over everybody that is not equal. Oops. So exclamation mark equal is not equal in Python, so it's going to be not equal to I. And this we're going to do for I in numpy arrange length. Yeah, so basically what this says is look at the vector Q, take from this vector all the elements not equal to I. So when we first loop, it's firm 0. So I'm going to take all the elements here except the first element, so the 0th element. And I'm going to sum it. So that's the Q other for firm 0. Then the second time that we loop, we do this for I in all these 0, 1, 2, 3, etc. I'm going to sum the output levels of all the firms except the one indexed 1. So that's what we usually call firm 2, etc. Yeah, so this will indeed return to me Q other that I'm going to be using here below. So Q other 0 is going to be the first element of this return statement, which is the Q other of firm 0. It's the sum of output levels of all firms except 0. So we have defined the fixed point. So now we can define the solution. And the solution, the equilibrium, is only going to depend on C because all the Q's, all the output levels of the firms are now endogenous. So this is going to return, again from SciPy optimize. I'm using f solve. Again, it's a lambda function because we're solving fixed point with x and c, and c is the vector that we give when we call the function. So we gave the function, now we have to give it a starting point. Now before we gave it a vector with 2 zeros, but at the moment I don't know, of course, how many zeros I'm gonna need. So I can use this function, numpy function zeros like, and basically it says take the vector c, yeah, whatever its shape is, and give me a set of zeros that has the same shape as c. Yeah, so if C contains 5 firms, 5 different cost levels, then this expression NP0s like is going to be a 5-dimensional vector with only zeros. So now we're going to define costs, and we're going to use the same trick as before. We're going to have these random draws, random from a normal distribution. So let's say I'm going to look at the case with 3 firms in the market, but feel free to play with this. I'm going to have 50 draws, so 50 different states of the world. The cost level is going to be on average 0.15, and I'm going to have a standard deviation of 0.05. And I'm going to use the NumPy representation of this call to TensorFlow random. And then I can calculate solutions. And that's going to be, let's say I'm only interested in total output this time, so I'm going to sum. And then I'm going to have the solution of costs. So there are 3 rows, which are the 3 firms. I want to have all the rows, and I'm going to index the i's. Oops. And I want to solve this for I in range. And we did 50 draws here, so I'm going to use range 50 here as well. And then to check whether it all worked, we can print solutions. So now if we run this, indeed I get a vector with all the different total output levels for each of the 50 simulations that we did. Yeah, so if you're wondering how long this thing is, there are 50 elements in solutions, which corresponds to total output. Yeah, because we take the sum for each solution. So for each solution I have 3 output levels, because I'm looking at the case with 3 firms in the market. I sum these, so get total output level for each of the 50 simulations that we run. Yeah, so in this way it's a bit more sophisticated, but it's a lot more flexible later on if you want to experiment with different number of firms in the Cournot market.